apparently we're ready. How's it going, folks? Sorry for those that were on the boat last night and making you come to a 9 a.m. talk, but I promise it should be fun. Hands up if you know what that is. Keep them up, keep them up. Hands up if you've got one. Put them down if you haven't. And keep your hand up if you did this with it, and that's where it's living. You know, not many, but hopefully we'll get it out of the drawer. That's the plan. The obligatory About Me slide. So I'm an application architect manager at Avanade in the UK. And I have been doing this for as long as you can see my hair has gone grey for. So, since before there was an IoT in 1999, making stamp book vending machines that we could dial into and pull out audit records and things like that. But really, I like the fun side of IoT, and that's kind of what this is. Really, it's a sneaky talk, and you'll see why at the end as well. I've also got 2 little girls at home, and so being a STEM ambassador is pretty important to me, and also just coming out into the community and spreading the love of physical computing and stuff like that. What's this? Go away. We don't want you. Sneaking up in my talk. So what are we going to be doing today? We're going to be talking about .NET 8 and what we can do with that, and how we can install it on the Pi. And then we'll look at the Raspberry Pi GPIO and the circuit. And then a little bit after that, we'll do what is commonly known as Hello World, but for IoT type environments. So flashing an LED, if you've ever done this before. And then we'll look at how we can use somebody else's code to be able to drive some extra components we've connected to the Pi. And then after that, we'll start talking about Blazor and SignalR and how we can move things around. And then we'll do some final wrap-up demos and a couple of bits of surprise on there. The slides, they're all online. There's going to be a link at the end as well, so don't worry too much about taking stuff down, but there will be some interactivity in a bit as well. Also, shout if I go too fast or if things aren't big enough on the screen and all of those good things. So .NET 8, if you've not used it, or if you've used .NET and you've not used .NET 8, for instance, it allows you to be able to target any platform, and that's everything from IoT that we'll be talking about today to browser applications, AI, and mobile, and everything in between. .NET 8 itself really kind of just feels like an improvement cycle to me, although we do get things like .NET Aspire, but you can see that most of the rest of the boxes there are just improvements on what was already there, aside from the ability to be able to publish to a container, which is quite cool, actually, because you don't even need Docker to do that, so I quite like that. Something I quite like, actually, is this slide. So most of it, aside from the one that's starred in the bottom right-hand corner, is from last year's .NET Conf. I like the one with a star in it, which is a bit of an older stat, but 40% of students are the people that are new to .NET. So I quite like that because .NET needs some love, and if you want to do that, you need to start early with folks. And I know universities and colleges, and it tends to be Python and C++. So to see .NET making its way into universities is good. I like that. So getting .NET installed on a Pi is non-trivial, shall we say. There's a lot of steps you've got to be able to do, and you've got to kind of know your Linux and Bash to be able to get a lot of it on there, and even then, you could trip yourself up. So I created a single-line install script to help. So you can see all the steps here. You just run that single-line script, and that will put .NET 8, full SDK that is, on your Raspberry Pi. Again, the slides are online, but do, by all means, take a copy of that. Also, don't just run scripts like this when speakers tell you to, because, you know, Bitcoin. So, I need the money. No, I'm kidding. So, GPIO. This is a way that you can control all of the electronics that you want to connect to the pins on your Raspberry Pi. To do that takes a little bit of code, but luckily there's a NuGet package, that's system.net device.gpio NuGet package. And that actually gives us access to the basic I/O, so inputs and outputs, but also things like serial peripheral interface, that SPI, PWM, pulse width modulation, which we'll talk about shortly, and other things like I²C. Again, these things are non-trivial if you don't have somebody else's code to do it, so this is a good thing. It supports the Raspberry Pi. Sadly, it doesn't support the Raspberry Pi 5 entirely at the moment. Still, which is a shame, it supports just on-off type stuff, LEDs and reading buttons, but it doesn't do anything else because they changed the whole architecture from under us when they made the Raspberry Pi 5. So Raspberry Pi 4 and under, and everything's going to be good for you. It does support some other boards, but just don't bother. Just stick with the Pi. It's so much easier to get these boards. Onwards from that, you can do something called Windows 10 IoT. Does anybody remember this? Now, this isn't the IoT flavor of Windows 10 that you see around, or Windows 11, the enterprise type Windows 10. This is a version that allowed you to be able to target XAML apps at the Pi, and it's quite old now, not supported. Don't bother using it. If you want to do anything beautiful on the Pi, just use Uno platform. It's wonderful. Go ahead and use that. So, again, limited on the Pi 5, but don't need to worry too much about that. Who's actually started plugging stuff into a Pi with those people that had the hand up? A fair number. Good, that's all right then. So for those that don't know, GPIO is a bunch of pins on the side of the Pi here that allow you to be able to plug in things like LEDs and buttons, but also a bunch of other components. And you can see on here we've got things like power, and we've got transmit and receive as well. So some of these pins are multifunctional. It's important to note there's two different sets of numbers on here as well, and that will become important later, where we've got the board numbering scheme, which is the one that's closest to the pin. And that top left pin, the square one, that's 1. The one to its right, that's 2, 3, 4, 5. I can count those pins dead easily. There's also the BCM numbering scheme, which relates to the BCM chip on the Pi, and that's a bit more complicated, and you're going to be converting from one number to another. Don't do that. Just stick to the board numbering scheme and be sensible. So that's good. We've got a basic Hello World circuit that I'll be beginning with, at least. So I've got an LED, a resistor, and a button. So on one side of the resistor, I've connected to my Pi on pin 10. And then the other side just connects to ground. And that resistor is just there to limit the amount of current that we pump into that LED, because you can break your Pi if you don't do that. It'd probably be fine, probably. But, you know, Pis aren't super cheap. Cheap, but not super cheap. Next to that, then, we've got on pin 26, one side of a button. Now, it's important to note there's no resistor connected to that button for those people that put their hand up. Often in these electronic circuits like this, you will need some form of a pull-up or a pull-down resistor to take that button to a known state. But actually, you can do that internally on the Pi. You can set what's called a weak pull-up inside the Pi, and that'll pull it up to a high value. Now, it's important, because when we start looking at the circuit, it's going to start to feel backwards, because when it's not pressed, it's actually high. And when you press it, the other side of that button is connected to ground, and it goes low. So the logic is going to kind of look a bit backwards, but that's why. So let's have a look. So there's lots of demos in this. Everything needs Azure, pretty much, aside from this very early part. I'm doing it all through the hotspot on my phone because conference networking. And it can go wrong. But let's hope it doesn't. So it should be good. It's all good. So the code, we start here. In the top left, we've got the NuGet packages. And you can see I've got some red squigglies because I changed branches too much. There's no typing in my talk. I'm just going to change branches. But that system.device.gpio, that is going to be doing most of the heavy lifting of what we're talking about here to begin with. And then down a bit further, we've got a console.writeLine, hello world, which might seem lazy, but actually it's super useful. And it's actually more useful on the next bit of the demo, in that this is a Raspberry Pi, so it's not a full-blown desktop computer. So when you build and run a .NET project, it takes a little while before it's actually finished, but it looks like it's doing nothing. We get no progress. So it's good to know when you're actually ready to do whatever you want. Otherwise, you're furiously stopping, starting, checking your code, and actually you're just trying to be too quick. So that's why I always leave those in. Next up there on line 14, we have our GPIO controller. And you'll see here that we're passing in a pin numbering scheme of board. So that was that board numbering scheme I was talking about earlier. You could use BCM. Don't. It would be a silly idea. And then below that, we have a couple of variables here. So pin 10, if you remember, we set our LED there on pin 10. So that refers to the actual pin that we're connecting it to. And then we've got a light time of 300 that we use a little bit later on. Now, if you try and set an LED on and then back off again, Pi is pretty fast. You're just going to get a slightly dim LED, so you need a delay in between the on and the off states. And that's what that 300 is. It's 300 milliseconds. Next up on line 25 down here, we take our controller, and then we use the write method. We pass in that pin 10, and we say we want a pin value of high. And then we've got that thread.sleep with that 300 millisecond wait. And then we do pin value low to turn it back off again. Another 300 milliseconds, and then we loop forever. It's happy with that point. If we exit, then we do a controller.close pin, and that just releases the function of that pin. It's just good practice. You'll see that there. I don't play much with that later. It's really just to show you that's what you should be doing. And that's the code. So there's not actually much code there. I mean, that's courtesy of having somebody else's code in this NuGet package, of course. So let's run that and see what that does, shall we? So what we're looking at is this. Now, this is wobbly normally, but we're on like a floating stage here, suspended in midair. So everything is really wobbly, so you can see it all wobbling around. Now, see what I was saying about, do we need that hello world? We have a hello world, so that's finished now. And what we also have now is a flashing LED. So it didn't take us very many seconds, actually, once we understood the concepts, to go from nothing to actually driving something using .NET on a Raspberry Pi. And with that single line install script, it even takes some of that pain out. So I'm happy with that. That means that we've got some level of control and we know what we're doing. So let's stop that bit of code. So next up, we need to do the second part of our demo, which is we've driven something out, but now we need to read something in. So I'm going to switch branches. Again, I'm not going to do any coding because I'm nowhere near that brave. So I could just switch between branches. And all this code's in GitHub, so you can go grab this code. Don't judge me. It's functional. The top of this code is identical. We've still got that system.device.gpio library. Downwards from that, we've still got our GPIO controller, but actually now we've got, on pin 26, we've got this button pin. So that is that same button pin that we had before, just there connected to our button, funnily enough. And then the next thing we do here on line 19 is that we've got a pull up. So this is this internal resistor that's taking our button pin to a known state. Happy with that. The code has changed ever so slightly here now, so we've still got a while loop. But now what we do is we read the status of that input, the button pin input, with that .read method. And you can see it's checking to see if it's false. And if it's false, then we turn the LED on. And then if it's true, we turn it off. So when I press it, it's going to be false. So it's going to kind of be backwards logic. But if you understand the circuit, you understand why that is. Let go of the button, the LED should turn back off again. So let's see that one. And this is the one where, you know, I could then furiously press my button and wonder why my code's not working and then spend half an hour debugging it when I was just overeager. So we wait for hello world. This is a Pi 4, the 8 gig one, so, you know, pretty powerful, and it's not a Pi 5. But it still takes that while to get going. So actually, this isn't the way you should go about developing .NET IoT apps on the device, but it can be quite useful because you can debug it there locally and get that fast development cycle. But you can do all this remotely, really. You can actually SSH in over a tunnel and debug locally. So that's actually what you'd end up doing. So now what I've done is invented a really expensive way to connect an LED to a button. And not only in actual parts, but time as well. But we can see we can press the button now and the LED comes on and off, which is great because now we've got control over both the inputs and the outputs. And you're rocking and rolling now because you're able to control things in the real world. So the world actually is your oyster at that point. So let's move on a little bit. To go even further than that, we need even more of some people's code because life starts getting complicated after that because you want to go connect some extra components, but they've got their own standards, their own formats, their own protocols. Luckily, some folks in the open source community, begun by Microsoft, have created this IoT.device.bindings NuGet package. And that supports a bunch of different components, like a whole heap, actually, including, and if you've ever seen me and my good friend Cliff Aegis talk, temperature and humidity sensors. Please, for the love of God, don't start with one of those as your next thing. That's the most boring thing you can possibly do as an IoT project. Because now you look like an idiot blowing on a little tiny component and going, oh, it's gone up by 2 degrees. 20 minutes for it to come back down again now. It's boring. There's far more interesting things to do. Look, robots, for instance. But every single IoT tutorial you'll ever see of that will be the next thing you'll do. So yeah, if you knock yourself out, if that's what you think you should be doing. There's only a limited amount of GPIO on a Pi. So if you run out of that, then you can get these things, these MCP I/O expanders, and they're serial-based devices, and you can go ahead and plug a bunch of them in and control a whole heap of stuff if you really like. Not necessarily the way to do it, but you could absolutely do that. There are also these things called hardware attached on top hats. Has anybody played with a hat for a Raspberry Pi? Most people who've got a Pi have had a hat. Not many, actually. A couple. Did you know that there is a Raspberry Pi and a Sense hat on the ISS right now? Actually, there's been 4, I think. Tim Peake took a couple up there, Raspberry Pi 3s, I think, with the Sense hat, the original ones, and then they sent up Raspberry Pi 4s and the Sense hat V2. And what that allows kids to do is write code that runs in space. Well, I know it's not quite space, but it is space, let's be honest. And you tell anybody that they can run their code in space, and it's going to get you interested in what you can do. And I love that as a concept. Change the modality of what you're doing, and it's going to be a bit more interesting. Luckily for us as well, this supports servos, which are little motors, which are the little blue things you can see in amongst my robot arms here. And we'll talk a bit more about those shortly. Now, the circuit gets a little bit more complicated, but I'll go through it, and it's not actually that bad. I'm expecting that window to pop up again in a minute. I'll just close it. You can ignore that. What we've got on here, so let's just show you the top down again. We've got the robot arm, and then we've got these little blue servos. There's one hidden under the base here. You can see it just about on this robot arm here. And they're little motors that allow us to be able to move our robot arm around. But you need to control them. Now, you might get away with plugging them on directly into a Raspberry Pi, but that's another good way to blow up the pins on your Raspberry Pi. So don't do that. So you need an interface board, ideally. And that's what I've got here. So I've used this, what's called a Servo 6 board, but actually, and it's a bit difficult to see on the image, but you can just build your own circuit. Really what you're doing is separating the power element from the control elements. So you can just buy that and start plugging your servos into it. But you need to connect it to your Pi still. So again, we're using something called pulse width modulation, which I'll explain in a minute, but the Pi has got pins for that. Pin 25 is one of those pins, and pin 35 is another one of those pins. But actually, we've got 3 different pins here, pin 13 and pin 12. So actually, pin 25 is ground. Pin 12 isn't a PWM pin. That's just a regular GPIO pin. But luckily, those people that wrote that nice device bindings library have made it possible for us to use software to drive PWM, which is actually quite hard. So worth noting, because you'll see that in the code. The servos will just plug into the other side of that interface board. So you can see just about there, actually, that yellow wire could be orange on your servo, depending on which one you get. That's the control wire. That's the one that's telling it which way to go, to move. And then we've just got power and ground like any component needs. You can't really plug these in the wrong way. You can, but it just won't work. It won't blow anything up. It'll just go, oh, that doesn't make sense to me. So a servo, and I've mentioned them a few times, this is what's actually going to allow us to move our robot arm forwards and backwards. It uses something called pulse width modulation. Does anybody know what pulse width modulation is? Geez, I can't see a bloody thing here. Quite a lot of people. Nice, that's good. For those that don't know, what it does is, if you send a short pulse and a long gap, the servo will go one way. If you send a bigger pulse and a slightly smaller gap, it will go to the middle, say. And if you send a big pulse and a small gap, then it will go the other way. This is oversimplification, but that's generally what it is. Actually, if you look on a scope, we're talking about minute differences in the size of those pulses. And the servo is actually kind of floating in that position, so you've got to maintain that really good pulse width and pulse so that it doesn't jitter around all over the place. So it's quite difficult, which is why that software defined PWM is actually quite impressive, because if you've ever tried to do anything with high-speed timing with an operating system in the way, you'll know that's hard. So they've managed to figure out a way to bypass the operating system on the Pi to do that, which is quite cool. So let's make our robot arm dance. So I'm going to switch to that branch. Move servos. And I'll just quickly go through the code and explain how that works. Go away. So we've got a few more usings here. We've got the device.gpio. We still need that. But we've also got device.pwm and device.pwm drivers. So this is coming from that GPIO package. That gives us access to pulse width modulation specifically. Then we've got the IoT.device.servo motor NuGet package, if you will, NuGet using. That's coming from that device bindings NuGet package. That gives us the facility to be able to convert essentially a frequency that you've got to give it into an actual angle. So we can just tell it an angle, and it's far easier than dealing with all of that maths and timing that goes on underneath that. So scrolling down, still got our hello world, because I like to leave that in there. But now we've got a PWM channel here. Now the code is repeated 3 times, but the last one's slightly different. But the first thing we do here is that we create a new PWM channel, and we pass in first the chip number. So the Raspberry Pi's got 1 chip to do PWM, and then we pass in the channel in that chip. And that chip has got 2 channels. Everything is 0 indexed, so chip 0, channel 0. And the 50 is just a duty cycle. Leave it at 50, don't touch it. Below that, then, we create our actual servo motor that makes use of that PWM channel just there. And we pass in the degrees of freedom. You can get servos that are 360 degrees or servos that are 180 degrees. These are 180 degrees, otherwise the wires will be terribly wrapped up and it looks silly. So it just goes between 180 and 0. Onwards from that, you can choose the maximum and minimum pulse width, and you can use that to tune the end stops of where that is in case it's kind of just moving around in the middle. These servos are cheap. That means not necessarily very repeatable, but you can get a bag of them for about a tenner, maybe 5 in a bag, depending on where you get them from, maybe AliExpress, so double that. Below that, we've got the exact same thing for the other channel. So the only difference between those two is the 1 in the right-hand side over here. Everything else is the same numbering, obviously. Below that, though, we've got our software PWM channel again. We've only got 2 hardware PWM channels. You tell it what to do, and the actual hardware deals with that frequency. Software side, more difficult. But the only part you really need to worry about on this is this true in the end here. So if you make sure you've got that true when you do it, and don't do like I did and leave it off and then wonder why the whole thing doesn't work very well, that true puts it into like a high-speed timer mode. So that is this bypassing of the operating system. You'll need to do that. You'll need to make sure it does it. After that, it's exactly the same. So we just use that same software PWM channel like we would normally. I fiddled with the numbers a little bit just to get it to balance software against hardware. So next up, then, we take our servo motors and we start them up. And then another loop, of course. We've got a loop. Now, we do this move to angle, and we pass in a servo motor from above. So we've got our servo motors above. And the angle I want it to move to. Now, that's just a routine I've got at the bottom down here that just makes my code easier later. But I just take that servo, and then I call the right to angle method. So pretty simple, actually. Don't have to worry about frequencies. Don't have to worry about any of that lot. We just tell it what angle we want to go to, and it will go there, which is nice. So I do that a bunch of times, which is why I was saying let's make my robot arm dance, because it's going to exercise all of those different servos and make them dance around, which is nice. So let's do that, shall we? You can stop your servos at the end, of course. That's important, actually, because otherwise it kind of sits there making noise, and it's just frustrating. So let's run that. And we cross our fingers, of course, and hope that I've put the batteries in and turned everything on. Has anybody done anything like this before? Wow. That's impressive. That's cool. I must talk to you in a little bit and see what it is you're doing. So what this is, in theory, doing now is it's going one way and the other way on the servo, on each of those 3 servos. So some of you might be able to just look at the real robot arm, but for the most part, you should be able to see that up there. It might disappear off the edge of the image a little bit. But nonetheless, actually, in not too many lines of code, and not too many steps away from just flashing an LED and reading a button, we're moving an actual robot arm now. Now, again, if you've got kids, they love this. Actually, what they do is they put their finger in there and go, ah, it hurts, Daddy. They love it. They think it's like an alligator or something. Ask me how I know. But I mean, when I got that far, I thought, this is really cool. And I could have just stopped because, you know, done, yeah? No, let's not stop there. That would be boring. So, good. Sometimes when you stop it, it kind of stops in a funny state and it makes that horrible noise, and I have to listen to that whole thing the whole time. Next up, if you've seen any of my talks, come on, where's this window? I'm expecting that window to have popped up by now. If you've seen any of my talks previously, or you've spoken to me or seen me talking about stuff, nearly I'm always talking about things like IoT Hub, or lately IoT operations, or digital twins. If you want to move a robot arm, really you want to do it in real time. You don't want to set it and then wait, and then it moves. That would be boring. So I needed a way to be able to do that. And actually, when I started writing this talk a while back now, Blazor was the thing to use. It still is, actually. And in fact, I've got to say that because the guy that created it is actually here. This guy over here, Steve Sanderson. I don't know if he's actually in the room, because that would be entirely embarrassing. But he just invented this Blazor as a way to get rid of JavaScript out of web applications. So this is a SPA framework, essentially. And yeah, the bonus is that now you're going to run everything in .NET, which is nice, because if you're a .NET house, then you don't now need JavaScript devs and also JavaScript. And it's plugin-less, so this isn't Flash, this isn't Silverlight. It just works in all of the major browsers, unless, you know, just Apple. I don't know. Depends on the day, doesn't it? You also then need a way to be able to send real-time messages backwards and forwards between a web interface, in this case, to begin with, and the Raspberry Pi. Now, SignalR is a WebSockets-based real-time messaging system for web applications. And it was created by these 2 glorious people who I've met a few times. Actually, they're such nice people. And it's old now, so 2011, in fact. So it's been around for a long time. And I think a lot of you may have used it and didn't even realize it if you're doing things like Blazor Server, because essentially that is SignalR under the hub for Blazor Server. That's actually allowing that communication between the DOM and the server end. It supports WebSockets at the top level. That's going to give you the best experience. And then downwards from that, you'll get things like server-side events and long polling. So if you've got networking restrictions, it should just cope with that. You don't need to worry about it. And like a lot of stuff at Microsoft, it's now open source as well. So go contribute if you want, which is cool. But also you can see what it's doing, I guess. I like that. So let's actually move our robot arm in real time from a browser. So stop. Okay, our code's already stopped, but we need to switch now. I'm just going to switch all the way to the end. There's actually a bunch of steps. If you clone this, you'll see it. And there's a workshop that goes along with it, and it'll kind of give you everything. The 3D print STL files for both of these different types of robot arm are there. Detailed list of where you buy all the parts, all of that stuff. So you can go do all of this yourself. But I'm going to switch right to the end and just quickly go through the code. The code won't change all that much, funnily enough. Wait, there we go. So we've got mostly the same sort of stuff here at the top level, where we've got all our servo motors, PWM, and the goodness that comes with that. But now we need to bring in HTTP and SignalR. We'll need both of those to make this work. The next thing we need to do is create a hub connection. So this is going to manage the communication between our device and the SignalR hub in the cloud. Shh. You get in on the act. We've still got our hello world because important. We've still got our PWM channels because we want to move the robot arm, and we still start them up. But the next thing we do is this block of code here. So we need to connect to where the SignalR hub actually is. and then we need a handler, and then we do a dangerous accept any certificate. Don't do this. Unless you really can't be bothered to try and figure out certificate issues. You can run this whole website locally, and so that means the Pi is talking to your machine and certificates. That makes life difficult. So you can just do this dangerous thing. I do like the fact they call it dangerous. Everything that's dangerous should be called dangerous. I like that. Mind you, that'd be half of the stuff that we'd be doing, I guess, but I like that. That makes sense. And then we automatically reconnect here as well. So if you have any signal losses, which is entirely likely with a setup like this, then we want it to automatically reconnect. It's not bomb-proof. It kind of works. And then we build that. That just creates that connection for us. And then if I Control-C out of this, because actually what's going to happen, this is going to run in a thread, and it doesn't exit properly. It seems garbage collecting things in the background. So if I Control-C out of this, I want to stop my motor. And that means that when I finish my talk, I can unplug it all, and it's not kind of, no, I'm not moving. And I'm going to break things. And I can dispose of things and exit and all of those things. Hey, look, see, my window's come back. Go away. It's not come up on screen. Good. So the next thing we do is, this is an event-based system. So SignalR works on, you declare a method that you want to invoke, and you need to handle that method when it gets invoked. It's kind of text-based. It kind of feels like this could be better, in my opinion. Maybe there is a better way, but this is the simplest way to use it. We've got a receive message. Now, who's used SignalR? When you did your tutorial, what did you do first? What was the tutorial? Was it a chat app? I bet it was. That's what this is. So all of these bits of code, all of these demos, I've done in a way that it should be one step away from the tutorial, pretty much. It shouldn't be too far away. So again, don't judge my code. Really, I've left it in a state that you can sort of see that, look, that's not actually hard to go from a chat app to this. So what I've got is, I've got a receive message, which would be a chat message. The user, in this case, is a servo that I want to move, and the message is the angle I want to move it to. So relatively straightforward. And then I've just got a bunch of ifs for which servo it is. I could have done this better. It works. And then I've got my move to angle function here. And then that takes in the servo motor I want to move, servo motor 1 in that case. And also I convert that message, which is a string, to an integer, and we're able to move. I'm sure I could have parsed that in the function. Don't worry. It's all good. And then I write it out to the console so I can see what's happening. And then at the end of that, so we must define our handlers for our invocations before we actually start the connection. We can do that start async. And then we do nothing else. We just sit there and wait for things to happen. There's our move to angle. So let's run that. And while it's doing that, I mean, you could just look at this, but actually what I've got is a Blazor application. I will briefly show the code for the Blazor application, but I don't want to bore you with loads and loads of code, really. This is the interesting part. So I'm projecting in the overexposed image of the robot arm, but you can pretty much see what that's doing. So what I've got here is the ability to be able to rotate my robot arm. Both robot arms, you see. Reach and grab. Now, grab's a little bit more difficult to see, especially when the camera's not pointed at the part you need and it's overexposed. That's a little bit better. So you should be able to see that part of the robot arm move when I change the grab. There you go. You pretty much see that, yeah? That's the part that gets your kids excited. So now we've got real-time control over our robot arm. We can move this. Now, it's interesting when you go to Australia and do this and realize that you've deployed this in Europe, and latency becomes a thing at that point. Real-time, is it? That seems quite slow, Pete. Luckily, North Europe, this is deployed in, so it's pretty good. But it's still going through my hotspot, so it's not perfect, but actually it's pretty responsive. And, you know, the code is basic, so there's way better ways to do this. In theory, you know, you move between two states like that, you should have a nice curve as it goes there, and I don't do any of that because it would be too complicated. But actually now what we've got is the ability to be able to control our robot arm from anywhere. And actually the first time I gave this talk, one of my friends had moved to New Zealand, and he was able to go ahead and move this robot arm from New Zealand remotely, and it was pretty responsive, actually. And then I later found out just how responsive when I went to Australia and did this. not too bad, actually. I mean, I know it kind of seems a bit silly, but actually, you think about like remote medical applications, this is exactly what they're doing. They're doing it better, obviously. Please don't operate on anybody. It's going to end badly for somebody at that point. And I could have stopped there, of course, but that would have been boring as well. So I didn't want to stop there. I'm going to leave it running. And I turn to my slides. Unity. You may have seen I have, and I keep saying Oculus, MetaQuest 3 here. Kind of like that whole X-Twitter thing. I always wanted to try making applications for VR, and I thought that this would be a really cool way to do it. And again, that's kind of what drives me to do this sort of stuff, is that I just want to be a geek and also want an excuse to go buy stuff like this, and my wife doesn't mind as much if it's for work. So if you want to go do any VR stuff, there's a bunch of different ways of doing it. But actually, if you want to do .NET development, then you can use Unity, which is great. So this is a cross-platform development platform for VR applications. And it's been around for a long time, actually. It's been around since 2002, and holy Lord, that's a long time. So that's as long as .NET, which is impressive, actually. It's struggled here and there. I think it's struggling again now. I think funding is probably a problem for them. I'm really hoping they don't have some sort of an implosion, because I love it. It's so good. It's used all over the place. And you can script in .NET Standard 2 or C# 8, which is pretty up to date. I know it's not all the way up to date, but it's pretty up to date. It's pretty good. Not only does it support VR, but it also supports, importantly for my demo, mixed reality as well. Actually, the original version of this was just VR. And then the Quest 3 came out and gave us mixed reality, and it was like, I'm definitely upgrading that. And when I did, I realized that I'd not touched it in 3 years, and nothing worked. And I had to start again from scratch, which was interesting, because I'd forgotten everything, because it was more than a day ago. You can plug it into your PC and deploy it directly as well, which is nice. So that development loop is pretty fast. One of the biggest problems I had is actually getting NuGet packages onto this, because there isn't like just an interface that you can add a NuGet package. You've actually got to go find the NuGet packages, find the bits of the NuGet packages that you need to deploy to ARM devices, and then do that again for the one that's dependent on that, and dependent on that, and dependent on that, and then get them all into your application. There must be a better way, but I didn't figure it out. In fact, so much so that you see people creating scripts that will install their NuGet packages for them. And the repo is in my GitHub. Actually, I don't think I put the link to it, but you'll find it in my GitHub repo. And there's a script in there that shows you how to get the NuGet packages in there so that you don't have to cry in the middle of the night like I did. So let's do that, shall we? Right, this bit's quite fun. So I'm going to go over to this part of the browser, and I'm going to put this on. Now, I don't know how that's going to work with the headset. Let's see. Hopefully it won't interfere. And then I'll cast to this page, and you'll be able to see what I can see. Can you see what I see? So, there we are. Who's got a Quest? Anyone? Fun, isn't it? I bet you just play Beat Saber. I like the golf, actually. Walkabout Golf's pretty good if you've not done that. Right. Now I can cast this. Next. It's not a very good look of the Oculus Quest on your head. Especially if you've not got a round head like mine. Right, can you see that? Can you see the what I can see? You should be able to see some stuff. If I make this a bit bigger, it will help. And also, if I resume this, you should see, in front of your very eyes, actually my eyes, a virtual robot. So this is, you can just download this model, and then it actually gives you access to be able to move it around, which was cool. So you imagine this was VR originally, and all I could see was the robot. I couldn't actually see anything else. It's pretty dangerous when you're on stage, because, yeah, necks and broken. And you need a way to be able to control this. Obviously, I could, in theory, go and move it with the web browser, but that wouldn't be any fun at all. So, with my very hands, I can create a menu, and I can move my robot arm from VR, and you can see the mixed reality robot arm is moving, and the real robot arms are also moving in tandem. Now, this one here is an ESP32 running something called .NET Nano framework, and that lets you run .NET on tiny little devices, which is super cool, but it is a tiny little device. So it has next to no power. So trying to get it to do a big, long sequence of SignalR messages is almost impossible, so it lags behind. And I've long finished my talk by the time it's finished catching up. But if you kind of just give it a jolt, a single message, then it's not too bad, it can do that. So that's why that one's slow. But this one, it should be pretty responsive. It's not too bad. But you know what's fun? I go back here. Scan that QR code, and you can move it too. And I've done this many times. And audiences are hooligans. I fully expect this to wave around and do all sorts of, here we are, so that was fast. This was actually super important for me when, look at that, I told you, hooligans. Hey, hey, hey. I know you are. You're here all day. You can't run. This was super important because I couldn't see anything but my robot arm, so I kind of needed some help. But you can sort of see now, actually, not only have we got a real-time controlled robot, we've got a collaborative experience here. Now, obviously, there's many different ways you can do this. I've run this as a workshop for Microsoft, actually, and that was really fun because we had people from all over the world, 3 or 4 different places, and they all went ahead and they built their robot arm, this version of it, actually, but with a Raspberry Pi connected to it. Yeah, this thing really has seen better days. It's literally been around the world twice. Oh, dear. Terrible. But what was fun was that everybody connected their robot to the same SignalR hub, and we had dancing robots that were all doing exactly the same thing across the world. It was actually pretty cool to watch. Yeah, I like that sort of thing. So that's fun. All right, stop it, you lot. Stop. Right, let's close that. Hey. Naughty people. Once we've done that, we've got SignalR, we can do that anywhere now. So, in theory, mobile app. Let's do that, shall we? Hold on, go back this way. I have a Maui app that I've created. Who's used Maui? You people, good. My friend Cliff would be annoyed because that's what he loves to do. So, I'm not casting my phone to the thing because that's just too clever, not doing that. But this is a Maui app, and it looks very, very similar to that Blazor app, and there's a good reason for that because the code is almost identical. Not quite. If you've done Maui, you'll know it's not quite the same. But I can move my robot arm around in here, and it does help that, you know, folks have moved it and it's a bit broken, but, you know, in theory that works. There we are, it does work. There we go. There we are, reach, rotation, grab, all those sorts of things. So that's great. But once you've got that far, no talk. In fact, I'm pretty sure you're not allowed to speak at events these days unless you mention the word AI. Oh, just once, I'll mention that. So, and I'm not going to do OpenAI for this because who wants OpenAI involved in a robot arm? Not me. It's not for me. But you can also make desktop applications with Maui applications, so I did that. And that start up. Control the robot with our voice. That's going to be quite interesting, really, because it never really works very well, but, you know, licenses. So, rotate by 20. Reach by -100. Oh, begin listening. Reach by -100. Rotate by 100. You see, AI. You get the idea, though, yeah? So that's using the speech API underneath this. So once you've got access to this stuff with .NET, you can do whatever you like. It's pretty cool, actually. And again, physical computing is a really good way to get folks into computing in the first place. So young adults, children, old adults, all of those good things. So it's good. I am annoyed at this, not doing that. But then, you know, what do you expect? I'm surprised it's not hallucinating. So, there are some links. Hey, come on. There are some links in a minute. What we've done, though, I've very sneakily given you a talk on .NET Everywhere. And it is, because I've ticked every single one of those boxes. Not very well in some cases, but I have nonetheless ticked it all the way from just IoT. I've given you a web app, deployed in Azure in the cloud, given you a desktop app, mobile app, gaming is Unity, of course, and AI, in brackets. Poor interpretation of AI. So, it's not always easy. My sadly dearly departed cat, she loved it when I was playing with those servos, so she used to come up and jump on the desk every single time. If you don't do things right, then it can get very jittery like that. And in fact, it can get really jittery after a while. So you're having lots of fun moving things around, and yeah, fasten it down. I ended up 3D printing this little base for it. So the reason I keep that in there, actually, it's obviously funny, reminds me of my cat, which I like. But it takes a little while to get used to this thing. So don't expect to just be an IoT genius as soon as you pick it up. Having a talk like this, having somebody else's code, all of those things help. You will break things. The good point of all of this is you get the right Raspberry Pi, you blow it up. Damn it, got to buy another one. Oh well. Most of it will probably still work. Use it for Kodi or something like that. But this is quite cheap. You can iterate on these things, and probably you shouldn't worry too much about blowing it up. There's a whole heap of links. That QR code will actually take you to the GitHub and the workshop. So by all means, that'll take you there. You'll be disappointed there's no slides if that's what you think is going to be there. I've got a blog post on how you can install .NET 8 on a Pi and then start controlling LEDs and buttons and stuff like that. That GPIO NuGet package, that's that third link there. The fourth link is actually a link to the source code for the device bindings library. Now, the reason why I link to that is because that's where you can see all of the devices that it actually gives you access to, and it's a lot. It's a really cool library, that is. The large 3D printed robot arm that we've got here, I don't recommend you start with that, to be fair, because it's a bit of a pain. You've got to get all the right nuts and bolts and stuff. I mean, it's kind of, I wouldn't even call it cool, but it's kind of cool. So do, by all means, but it's just more complicated. Better off printing this one, which you can print flat, and it's a little bit janky, but blame going to Sydney and back, that's all. But what's good about this one is you can plug all the servos into the 3D printed parts and just screw the servo into it, and you're done. So you don't need to worry about nuts and bolts. The servos will come with the screws, so you're off and running. It was actually designed by, and I've mentioned him before, Cliff Aegis' son. He designed the 3D STL files for that and let us use them. So, hey, it's either my Quest or one of you lot, malfeasants. But hopefully, if I've given you some impetus to go out and try IoT, that's great. But contact me here by all means. Don't worry. The worst that can happen is probably that. But even that'd be fun, because that's where the magic smoke comes from when things happen. I don't think I've ever seen it do that. I'd be very worried. Don't blow yourself up. That QR code there, that will take you to the slides. By all means, go ahead and do that. Reach out to me. I love people tweeting me and saying they're penniless now because they've gone out and bought a load of IoT stuff, and that happens all the time, actually. Thanks, Pete. My wife hates me. Do that, and hopefully you enjoyed the talk, and thanks very much for coming. Appreciate it. Any questions? Anybody got any? No hands? Come see me if you've got questions. I'm here all day. It's my birthday tomorrow, just saying. Thanks, folks.